So the next speaker is Sayantan. Are you here?
Yes, can you hear me?
Yes, great. All right, you can share your screen. And Sayantan is a PhD student in the Intelligent and Interactive Systems Research Group at the University of Innsbruck. And of course, the primary research interest is in developing algorithms for lifelong continual learning and scaling them up for the real world, like for robotic application. And we may hear something about it in this talk, Continual Learning from Demonstration. So Sayantan, when you want, the floor is yours.
All right, thank you so much for the introduction. Hi everyone, I'm Sayantan, and today I'll be talking about our recent work on continual learning from demonstration. This is where we train a robot to perform multiple motion tasks in the real world. So I'd like to start by thanking my collaborators, Jakob, Antonio, and Justus from Innsbruck and Matteo from the University of Trento. Before starting, just a little bit of motivation regarding what I do and why I do it. So imagine that you have a robot and maybe you wanted to do some kind of task in the real world. Maybe an example can be opening a box. So after you've trained the robot to open the box, maybe now you wanted to pour coffee into a cup, or put the bottle on a shelf, or take the plate out of the washing rack. And all of these tasks involve different kinds of motions, right? It's not the same motion for every task. The position and the orientation of the robot, both of them need to change. A simple way of doing this might be that you train one model for box opening, one model for coffee pouring, and then you end up with 4 models. Or you could somehow combine all the data, use replay and multitask learning to somehow train the robot. But none of these are very scalable. And for me, this seems like an ideal scenario in which I can apply continual learning. So the objective is to use one model, train the robot for one task as the task arrives, so one at a time, and not to store any data. And so all the usual continual learning things, and to end up with a model that can perform all tasks. So first, let's take a look at how the robot can learn a single task. So this we do by a technique called learning from demonstration, where a human user provides a few kinesthetic demonstrations, like maybe 5 or 6 such examples. It shows the robot how to pour the coffee in this example. And we record the demonstration trajectories that have been given to the robot in the form of a data set. Here, this is just an illustrative example of a 2D trajectory, but in reality, it would be for both positions and orientations. And then, of course, we don't want to exactly replay what the human has done. We want to learn a vector field, such as that shown by the green arrows in the background. And what this allows us to do is to start from different starting positions and still end up executing the same trajectory that has been shown. And finally, if this is successful, then the robot can perform this, whatever motion the human has shown. And then the idea of continual learning from demonstration becomes very simple. We start off by training the robot to perform one task, and then we train it to perform another task without looking at the data of the past. And then we go on in this way. And at the end, we hope to have a robot that can, on command, perform any of the tasks that it has been trained on. So I'll be talking about 2 papers which try to achieve this objective. The first one is called Continual Learning from Demonstration of Robotic Skills, and this was published very recently. And to do this, we propose a couple of hypernetwork-based models. So here we have a hypernetwork that generates the parameters of a neural network known as a neural OD. So this is a dynamic assistance model that you can use to learn the vector fields that I spoke about earlier. But of course, if we just use hypernetworks, all of these parameters of the neural OD are generated from the last layer of the hypernetwork. And if this neural OD is a little bit on the bigger side, then the hypernetwork becomes very big. So we also look at these chunked hypernetworks, which instead of producing everything from the last layer, produce the parameters in smaller segments called chunks, and then we stitch them up to create the neural ODE. We compare these models against some baselines. So first is the simplest baseline, that we train each new task with a separate neural ODE. Then we look at the simplest form of replay, where we store the training data of all the past tasks and combine it with the new data. We also look at fine-tuning, where we just optimize for the current task, and we also compare with some other regularization approaches like synaptic intelligence and memory-aware synapses, which just try to protect the parameters of the neural ODE. Right. So for evaluation, the first data set we use is known as LASA. And this is a data set that's very popular in the learning from demonstration robotics community. And it contains a set of two-dimensional trajectories like the ones you see on your screen. So LASA has 26 of these different shapes in the 2D plane. And we treat each of these trajectories as a different task. So we give the models one task at a time. And after it has learned all the 26 tasks, I ask it to predict all of the past tasks. And this is what you see on your screen. So the first row is with the single model. So this is where each task is learned by a single neural ODE. And of course, it works perfectly. And we treat this as the upper baseline for comparison. But when you look at the results of the hypernetwork and the chunked hypernetwork, the regular hypernetwork also works almost as perfectly as the single networks. But the chunked hypernetwork kind of has difficulties with the, with the tasks at the end of the sequence. When we look at the continual learning metrics, here we compare the single networks in blue, the chunked hypernetworks in green, and the regular hypernetworks in red. You can see that the hypernetworks overall, they perform more or less well for most of the continual learning metrics, such as remembering and accuracy and so on. But the single network, because it is 26 networks taken together, the parameter size is much more, and so it doesn't do so well in these metrics. And when we look at the other baselines, it's also a similar story that all of them fail for one or more metrics, whereas the regular hypernetwork in the red is the one that has the overall best score. Next, we evaluate with the robot, and this is a data set where the robot is trained to write one letter at a time, so 7 letters. And then we ask it to reproduce these 2 words, hello world, after it has been trained. And here, because there are fewer tasks, so 7 letters, 7 tasks, the chunked hypernetwork actually performs best in, when you look at all of the continual learning metrics. Whereas, again, the other baselines fail for one or more metrics. But our real objective is to move this to the real world. So here we have a sequence of 4 tasks, which involve both the position and the orientation of the robot. And so like tasks like opening a box, putting a bottle on a shelf, stacking a plate, and pouring coffee beans from a cup. And we train this in sequence. And once it has been trained, we can ask the robot to reproduce any of the skills that it has learned. And with the hypernetwork as well as the chunked hypernetwork, the robot is able to do so. And when we look at the continual learning metrics again, here also the chunked hypernetwork is the one that has the best scores overall, because it does well when you consider all of the different trade-offs that go into continual learning. But of course, there are quite a few limitations. The first limitation here is the concept of stability in the predicted trajectories and in the vector field. So one common problem in this kind of learning from demonstration is that if the learning is not successful, there can be situations where the vector field kind of diverges away from the goal. So the goal is here, if you can see my cursor. And on the example on the right-hand side, if a robot were to follow this vector field, then it would reach the goal and then drive away from it. And this is not what we want. We want the vector field to converge at the goal so that the robot always goes to the goal and stops there. And the neural ODE does not have such stability guarantees. Another problem is that, for the LASA data set, we saw there are 26 tasks, and the chunked hypernetwork kind of starts exhibiting a lot of error after the 5th or the 6th task. So it can't really learn a long task sequence as well as the other two. Then there's the problem of, with hypernetworks, the training time of each new task increases as we add more and more tasks. And this is clearly a problem with the scalability of hypernetworks and limits how many tasks we can learn. And the last limitation would be that in this paper, we have only looked at either 2 or 3 dimensional trajectories, and we want to see how well this kind of method scales to higher dimensions and more difficult problems. And this is what we do in this next paper. This is still not complete, so my collaborators are reviewing this right now, but I still put a temporary version of this paper so people can take a look if you're interested. So first up is this concept of stable learning from demonstration. So to do that, we use this model that was proposed in this paper by Coulter and Manik. And here, the neural ODE has a simple neural network. So this is a nominal dynamics model similar to the neural ODE that I spoke about earlier. In addition, there's another neural network which represents something known as a Lyapunov function that enforces the stability of the trajectory that is predicted. And these two together, they are combined in a certain form, which I'm not talking about right now because of time constraints, but it's there in the paper if you're interested. The combination of these two things ensures that whatever comes out of this stable node is always a stable trajectory. So for example, when a stable node is initialized randomly, so this is not trained on anything, this is just randomly initialized, and I give it some inputs, this is the kind of trajectory that it predicts. Even a randomly initialized network predicts trajectories that always end up at the goal. For an untrained network, the goal is the origin, but like there's a theoretical guarantee that it cannot produce unstable motion. So then what we do here is we take the hypernetwork and ask it to produce 2 different neural networks instead of just one, as in the previous case. And we do the same with the chunked hypernetwork. And then the stable neural ODE is trained as in the original paper. When we do this, the most surprising thing is, of course, you expect that the trajectory will be stable and it will converge at the goal. But in our case, we saw that there are huge benefits to the continual learning performance. And this is the main contribution of this paper. That if you look at, when you look at the single networks, there is not much difference between using a node or a stable node. But when I look at the performance of the chunked hypernetwork, the one with the regular node produces huge errors after the 5th or 6th task, whereas the one with the stable node keeps on working till the end. As far as continual learning metrics are concerned, again, the red and the green are the hypernetwork methods. They work better than the other baselines. And when I compare the differences between node and stable node for chunked hypernetworks, you see that there is a huge improvement that the stability brings to the continual learning performance. Right, next we tested on several high-dimensional data sets. So here, each task is a 32-dimensional trajectory. So I plotted 2 at a time just for ease of viewing. But each task has 32 dimensions, and then we had 10 tasks. And the chunked hypernetwork was trained on all of these 10 tasks and then asked to reproduce all the past tasks. So here we can see that till the 8th task, that is task 7, it can reproduce quite well. It has some difficulty with the last 2 tasks, but still much better than the node that is not stable. And finally, we test it on the real world. So we extend the last data set of 4 tasks to 9 tasks. And again, we see that the chunked hypernetwork with the stable node has much improved continual learning performance. So here again, we see that there is a lot of improvement in the accuracy, also in the remembering and how much time it takes to train. So at the end of, okay, this does not load perfectly. There are supposed to be 9 of these. All right. So we have all of these 9 tasks that were trained in sequence. And at the end, the robot can reproduce all of the 9 motions, stuff like folding a mat or scooping with a spatula and flipping a table and so on. And finally, we also looked at the regularization of hypernetworks. So the hypernetwork regularization involves this iteration over the task embeddings, which causes the training time to increase. What we did is we removed this summation and instead just randomly sampled one task embedding in each iteration. And this gave us a model where we have the same performance, so same low errors, but the training time of each new task does not increase anymore, it stays the same. And yes, so for future work, we could extend this by adding visual inputs or refine the trajectories with reinforcement learning. But more interestingly, one could also think of some kind of a high-level planner which will combine all of these different motions to achieve different objectives. All right, that's it from me. Thank you very much for your attention, and I'm happy to answer if there are any questions.
Thank you so much. And nice to see this summary slide. It's very helpful. So do we have any questions for Sayantan? Otherwise, I can ask you one. I was curious about, do you have or do you see any future developments towards multi-agent? So in robotics, it seems that having more than one robot may be helpful, perhaps not in the robotic arm case, but in some others. So do you see this as something that the community of robotics is interested into with continual learning, or are you aware of any works, or are you interested into that?
As far as if you're talking about different robots doing different tasks, then I'm not aware if continual learning has been applied in this context. But I could easily imagine that you have 2 robots which work in a collaborative manner. Maybe you have 2 arms, performing different motions.
Yeah, that was my idea. Yes.
Yes. But continual learning for robotics is a brand new field, and I have a hard time in robotics conferences pushing stuff.
Okay. So. Yeah, that's also interesting to know, actually.
Yes,
okay,
because I think there is a huge amount of scope for continual learning in a robotics scenario, because these are resource constrained situations, right? If you want the network to work on the robot. And well, let's hope that people start appreciating continual learning a bit more in robotics.
Yeah, sounds an exciting use case, to say the least. So we are interested for sure as continual learning. All right, thank you so much, Sayantan, for this talk.